Okay then. So we've done a lot of work with sequences, so just going to do a little bit more today, and towards the end I'll introduce the next chapter on series, and maybe give a first example or two on series. Now you've got everybody has this sequences tutorial sheet. If you don't have a copy, I've got spare copies here, you can pick them up at the end of the lecture. If you don't yet have a copy, but this is on Moodle. So this is what you've been using. You've been using this as your main source of problems in the tutorials. Of course, there's also end of chapter exercises in the book of lecture notes as well. So you've got plenty of things to be working with. So in the tutorials this week, on my half, you can continue working on these sequence problems, any of these that you haven't encountered yet. But I thought today, since the tutors might necessarily be prepared for it because we just added it in at the last minute, I'd have a look at the squeeze lemma, the squeeze theorem. So questions 12 and 13 there are some more convergence results. And I made the comment last time that you'll be looking to probably construct epsilon n type arguments for these. And then we added in at the last time, I wouldn't say this list is exhaustive, or we covered each and every possible result you could frame about convergence of sequences. But one common one that's often used is this. It's called the squeeze lemma. We discussed it last time, a little bit. We introduced it. So the squeeze lemma is used when you're trying to prove the convergence of this sequence Bn. And what we might know about Bn is we might have a sequence An and a sequence Cn which provide lower and upper bounds for the term Bn. Okay. So if it's known that our sequence Bn that we're aiming at is always between terms An and Cn, and if in addition we know that An and Cn are convergent sequences, crucially that they converge to the same limit. So An is converging to L, and Cn is converging to L as well, it's the same limit L. Then, so the Ans are here, they're getting closer and closer to L. The Cns are here, they're getting closer and closer to L. All of the time, the term Bn is trapped between the An and the Cn. So if the An and the Cn are converging towards each other, where can the Bn go? Well, it can't really go anywhere. It's squeezed between the two sequences, An and Cn, and it must also be converging to L. Now, this kind of explanation with dancing your fingers around is pretty compelling, and it pretty much is the correct idea. But it's hard to kind of claim that that's a proof. It's a compelling argument, but what we would like is maybe just a more formal, careful proof of this. Okay? So that's what we're going to give now. And it's going to make use of the formal definition of convergence. And so this is the squeeze lemma. This is question 13a. We added it in last time. So we assume we have sequences An, which is converging to L, Cn, which is converging to L as well, as n goes to infinity. And for a third sequence of terms Bn, we have for all n An is always less than or equal to Bn, and that's always less than or equal to Cn. That's what we're assuming. And we have to try and prove that the Bn is converged to L also. And we want to do this with respect to the formal definition of convergence. So, given any value of epsilon, we have to show that there's some point beyond which the Bn elements are always within a distance of psilon of the limit to L. Okay, well, firstly we can use something that we've already proved. When you're constructing these theories and building up these proofs, it's always a good idea if you can, rather than always going back to first principle arguments, if you can make use of the things you've already proved, then that's quite an efficient way to work, and it makes use of what you've done. So we can make use of the algebra of limits theorem to show that the absolute value of am minus cm is actually convergent to 0 as n tends to infinity. And that's since, you see, what is the limit as n goes to infinity of am minus cm? Straightforward application of the algebra of limits theorem. See, we've assumed that am and cm are both convergent to L. So the limit of am minus cm is going to be the limit of am as m goes to infinity minus the limit of cm as m goes to infinity. That's true by the algebra of limits theorem. And these two quantities are both L, so this is equal to 0. Okay, that's not that astounding. If the am is convergent to L, the cm is convergent to L, it means the distance between am and cm has to be convergent to 0. It's pretty clear, but we can see it here as a nice use of the algebra of limits theorem. The limit of a linear combination is just equal to the same linear combination of the limits. And now we can go for sorry. Just had a short moment. Okay. So now we let epsilon be greater than 0, be given. And we know that there exists a number n1 such that for all values of the index m greater than or equal to n1, we know that the absolute value of am minus cm is going to be strictly less than epsilon over 2. And there exists another number n2 such that for all n is bigger than or equal to n2, that the absolute value of am minus L will also be strictly less than epsilon. Now, these are both true because these are both instances of the formal definition of convergence. One for the sequence am convergent to L. Am converges to L. That's one of the assumptions, and the justification here is since the distance am minus cm is convergent to 0, which we just proved. So now we can look at the distance between, so now we can let n be the maximum of these two numbers, n1 and n2, as we usually do, because we want to make use of both of these inequalities. And now we can say that for all values of the index little m bigger than or equal to n, both of these inequalities are true. And this is going to help me deal with the distance from Bn. This distance, Bn minus L, this is the distance I want to show is small. This is less than epsilon. Because this, if I do that for every epsilon, then this will show that Bn is convergent to L, which is the conclusion we're trying to get. And I'm going to do this by saying that this is equal to the absolute value. I'm going to first judge the distance from Bn to An, and then look at the distance from An to L. So I'm just simply adding and subtracting N in there. So I'm not changing this quantity. But by the triangle inequality, this is less than or equal to this absolute value plus this absolute value. Now remember, the Bn's are always trapped between Am and Cm. Yeah? So the distance between Bm and Am has to be less than or equal to the distance between the two endpoints, Am and Cm. So this distance here, the distance between Bm and Am, I can say is less than the distance from Am to Cm. So this is still Am minus L. So this is true since Am is less than or equal to Bm is less than or equal to Cm. So the distance from Am to B, distance between Bm and Am is less than the distance from Am to Cm. This is just the triangle inequality. And now you see, because m is greater than or equal to L, I know this first value is strictly less than epsilon over 2, and this second one is also strictly less than epsilon over 2. So that's from above. Okay, because we know that n is greater than or equal to the maximum of n1 and n2, and when n is bigger than n1 and n2, both these inequalities. So this is our quantity epsilon here, epsilon over 2 plus epsilon over 2. So we have proved that for any value of epsilon, so I took a general positive epsilon here at the top, there does exist a point, capital N, and for every value of the index little n bigger than or equal to n, the absolute value of Bn minus L is strictly less than epsilon. So that's exactly the formal definition of convergence that we need to prove. Okay, so we would finish that proof then by just declaring that we've shown that the formal definition of convergence is true. So Bn does converge to L as m converges to infinity by the formal definition of convergence. Okay, so that's our proof of the Squeeze Lemma. I mean, it can be frustrating in a way because the very we had a nice, clear, simple explanation for the Squeeze Lemma. The AMs are coming this way, the CMs are coming this way, the BMs always trapped between them, and because the AM is converging to the same thing, the AM and the CM, the BM is always trapped between them, so it has to be getting closer and closer to L as well. That's a correct argument. There's nothing wrong with that argument. There's nothing incorrect about it. But, just kind of giving compelling arguments like that while they're good, but the question is getting it formally down on paper with respect to how you define things. That could be the trick. So it's a little bit unfortunate that we end up having to go to some quite technical arguments about manipulating inequalities and respecting the formal definitions. But at least that assures us that we have a rock solid proof of it, a very formal argument. So we can now make use of this squeeze lemma in many other examples, and we'll always have good faith in the results like this. Okay, so are there any questions or any clarification that you'd like on that argument? You may well find, there could well be simpler, more direct proofs of the squeeze lemma. You should look up, see what proofs of it or arguments for it you can find on the internet. You may find cleaner, more efficient ones than the one I've given here. Yes, question?
So is what we're trying to prove that AM and CM converge to be something like the aim of the question?
So the aim of the aim of the question see, it's if all of this, then this. So the aim was to prove that the BNs were convergent to L. Yeah. All of this information was assumptions. Those are the conditions. If we know that we've got two convergent sequences, AN and CN, if they're both convergent to the same thing, and in addition, they are always lower and upper bounding the sequence, the elements Bn from a third sequence, then the conclusion is that this third sequence Bn has to converge to L because it's being squeezed by the other two. Yeah. So that's the goal in all of this. So you use these facts to prove the conclusion. And see, that's how we structured it. We started off by assuming all that information. So assuming a sequence An converges to L and Cn converges to L, and assuming that our third sequence Bn is always trapped between. Then here, in this little argument at the start, we use the fact that AM and CM converge to L, and that proved that the distance between AM and CM is convergent to 0. So we could make the distance between AM and CM as small as we want. And then, so where did we use the inequality? Yeah, the inequality between AM and CM was used down here. When I used the fact that the distance between BM and AM would be no bigger than the distance from AM to CM. The BM is trapped between the two. The difference from some intermediate point to one of the endpoints is less than the length of the whole limit between AM and CM. So you should pick out in the argument where all the assumptions are used. The fact that AM and CM converge to L is used here. The fact that we have this inequality AM less or equal to BM less or equal to CM is used down here. And then in these parts here, see these parts here, we were using the formal definition of convergence. Using the formal definition of convergence to know that there existed these points N1 and N2. Where the distance between AM and CM reaches a certain smallness, and the distance from AM to L reaches a certain smallness. And then, remember our goal was to prove that the BM is convergent to L. So we were trying to prove that we can find a point, which is this point here, capital N, such that for every value of n bigger than n, Bm minus L is always strictly less than psi. That's the formal definition of convergence. So that's our goal here. So that's why I arranged that these two were smaller than epsilon over 2, and this distance I'm interested in is smaller than the sum of those two. Distances. So it's very much the same kind of type of proof as was the proof for the algebra of limits theorem results as well. And in question 12 and 13, you'll be looking to arrive at proofs along those lines, constructing those epsilon and n. So there's some work for you to practice with there. Now, in the notes, we didn't discuss in the lecture the proof of the quotient form of the algebra of limits theorem. The proof is in the notes, and I'd encourage you to read through that. Because it's again a psi and n argument, but there's a little twist to it in the fact that you're dealing with quotients. When you're trying to make quotient small, you have to make the top small, you have to make the numerator small, but you have to prevent the denominator from getting too small. So when the denominator gets too small, the whole fraction gets big. So if you're making a fraction small, you want to make the numerator small, but know that the denominator doesn't get too small. So that's discussed there. So I encourage you to read that as well. If you have questions about that, do either come and see me about it, or ask your tutor, or see any of us in our drop-in office hours, or Ryan, the program support tutor, in his drop-in office hours. Okay. The only other thing we didn't say anything about is L'Hopital's rule, which is at the end of chapter 1. And I'm not going to say a whole lot about that. You can read that at the moment. The reason is that it talks about the derivative of functions, and well, because we haven't formally discussed the derivative yet, we're working towards that. I'll postpone the discussion of L'Hopital's rule until that time. And we'll be able to give quite a good argument or good proof for the truth of L'Hopital's rule. Okay, this is where I'll just say something very briefly about it. When you're trying to judge the convergence or find the limit of a fraction of things, L'Hopital's rule can be used in the cases where the numerator part and the denominator parts aren't converging to some fixed limit, but are converging to plus or minus infinity. So are increasing without that. Or in the case where they're both converging to 0. See, in these cases here, we cannot apply the algebraic limits there. And we can't say that the limit of an is infinity over infinity, or that the limit of an is 0 over 0, because those quantities are nonsense. It doesn't make any sense to divide infinity by infinity, or to divide 0 by 0. They're undefined things. So the algebraic limits theorem does not apply, but what we can use is this fact, which is L'Hopital's rule, that the limit of the quotient, so we have here, the limit of the quotient, will be the quotient of the limits of the derivatives, provided those derivative expressions do converge. Okay, but we'll have a lot more to say about L'Hopital's rule when we're dealing with differentiation in detail. Okay. So for the tutorials this week, you should continue to look at any of these questions on the sequences sheet. And there are these extra convergence results to be working towards. There are dealing with various recurrence relations and questions. Well, I did 8 in the lecture last week, but questions 9 and 10 dealing with recurrence relations. Another kind of one in question 11. Question 14 is, kind of an extended exercise, but maybe not something to be able to do in the time space of a tutorial. But it kind of relates back to the induction activity we did, dropping our needles to estimate pi. This is a more analytical way of estimating pi, and it's based on thinking about the polygons, the regular polygons. These are figures made up of n straight lines. That the largest polygon, the largest n-sided polygon you can put inside the circle, and the smallest n-sided polygon you can put outside the circle. So as the number of n, as the number n of sides increase, these polygons get a better and better approximation to the circle. But we can, using various trigonometric arguments, we can arrive at nice recurrence relations for the areas of those of the outer and inner polygons. and they're good, good recurrence relations that we can calculate and evaluate just using the ability to extract square roots and do the regular arithmetic operations. So in that way, we can construct good approximations to the model. So there's a lot of guidance there, and it's a nice kind of extended investigation exercise. Okay. So in the remaining time, what I'd like to do is introduce the series chapter for you. I'll have another tutorial sheet of tutorial exercises on the series chapter, but since you're still working on the sequences one, for now we'll just do a bit of an introduction to the series. So series are related to sequences. So familiar with the idea of a sequence. A sequence is just a list of numbers, usually, sequence of numbers, just a list of terms. Series is when you add them all together. Now, if this was just a finite series of adding together 5 things, okay, if things were interesting, we might be interested in the sum. If things weren't interesting, we would be particularly interested in the sum. But where things really do get interesting is where we look at infinite series. Okay? So an infinite series is the sum of an infinite sequence. And we can use the capital Greek letter sigma. That's the capital or the uppercase version of the Greek letter sigma. And sigma is their S. The uppercase, that's the lowercase. So sigma is the S sound in Greek. We use that to represent the operation of summation. Okay? And these upper and lower limits, n equals 1 and infinity, they let us know that the sequence elements start at 1 and they go on without any. Now, the first question we've got to get over with series is, does such a thing make any kind of sense? Normally, or often, we think of summation, adding up numbers, as some kind of process. You might actually carry it out. You've got a list of numbers, you type them into the calculator one by one. It's some kind of process that lives in time. Or you give a list of numbers to a computer and it adds them up, apparently instantaneously, but it does take an appreciable amount of time. The computer is actually doing a sequence of steps that it needs to do to work out the sum, of course. So again, it's a process that happens in time. So well, when we first meet it, you could give a pretty strong argument that this notion is problematic, because how can you ever talk about some kind of process that takes an infinite amount of time? Surely that's nonsensical. You could never talk about the value of a process or the outcome of a process that takes an infinite number of steps. Okay? So there are philosophical obstacles or logical obstacles to maneuver around, so that you can be sure that we're talking about something sensible here. Before we before we look at the precise way we make this talk, we make these things sensible, we'll just consider a couple of examples. For our first example. Here we're going to sum from n equals 1 to infinity. And we're going to sum 1/2 to the power of n. So this is the sum. When n equals 1, you have a half. When n is 2, you've got a quarter. When n is 3, you've got an eighth, and so on. This is an infinite sum. We're adding up an infinite number of numbers. But of course, notice that the numbers are getting smaller. And by smaller, what we mean precisely is that the numbers we're adding up are converging to 0. Obviously, if the things you're adding up aren't getting smaller, then the sum is going to keep growing and growing, and probably grow without any size. So the sum is probably going to not have a finite value. The things you're adding up are not getting smaller. But if the things you're adding up are getting smaller, then maybe there's a chance that they do have a good, well-defined value. And this series, we can argue fairly simply that the sum of this series is 1. Because we can relate it to a process of simply taking steps across the room. So if I want to walk from here to the edge of the desk, let's say that's a meter distance. So I begin by walking half a meter, just here, halfway there. Then the next step I take is a quarter, which a quarter happens to be half of the distance that I have yet to step. So I step forward a quarter step. So the sum is keeping track of how far I've traveled from the start. I took a step of a half a meter and then a quarter. Then I take a step of an eighth of a meter, see, there's 1/4 remaining. So I've come 3/4. 1/4 remaining. So I take a step of an eighth, which is a half of a quarter. So I'm getting closer and closer to the desk, which is 1 meter away from where I started. But at each stage, I'm only stepping a half of the remaining distance. So I'm certainly never going to go past the edge of the desk. Okay, so I'm only stepping forward half of the distance that I'm away from the desk. So I'm never going to go beyond the desk. But because I'm halving the distance each time, I'm going to get arbitrarily close to the desk. If you want to see me any degree of closeness to the desk, if you just wait around long enough, you'll eventually see me get to that degree of closeness to the desk, because I'm halving the distance each time. And those halves, that means the remaining distance is converging to 0. Okay? So, it's not too hard to maybe appreciate that 1 is a good value to attach to that infinite sum. So, at least in some cases, it seems fairly compelling that we should attach a finite value. We should attach an outcome to this infinite process. Even though there's still philosophical problems about what adding up an infinite number of numbers is. How could you ever get the value? But there's a strong sense in which we should attach the value 1 to this. And we'll see later, this is an example, or a straightforward example, an easy example of something we call a geometric series. So it'll be completely untroublesome that it should have the value 1 later on. So in fact, we define convergence for series using the concept of convergence for sequences. So, what is the meaning of this thing? The sum from n equals 1 to infinity of a series of terms xn. Well, what we mean by that, so this is a definition. What we mean by that sum is the limit as k tends to infinity of a certain sequence. Now we've spent a long time discussing limits of sequences and convergence of sequences. We've got a very good understanding of that. We've got several results about how convergence of sequences behaves. So what's a natural sequence to associate to the infinite sequence? So a natural sequence to associate to the infinite series. Well, you kind of saw it as I was stepping across the floor. The sequence is looking at my intermediate progress towards the edge of the desk at each stage as I take my steps. Okay? The infinite series is the distance 1, what I complete with when I've done in my infinite number of steps. But the sequence you can look at is the sequence of intermediate stages. So we represent them quite nicely as the sum from n equals 1 up to the k of x. Now these summations here on the right-hand side, these are completely unproblematic from the philosophical standpoint. Okay? Each one of these things here is just a finite sum. You've just got some collection of numbers, x1, x2, x3, all the way up to xk, and you're just adding them up. Okay? It may take a long time to calculate it, but there's no philosophical or conceptual problem about these sums here. And they form a sequence. As k gets bigger and bigger, you've got a sequence of intermediate sums. And whatever the limiting behavior of that sequence, that's the value that we associate to the infinite series. Okay? So these things are called the kth partial sum. It's a good descriptive term for it. This is the infinite series, the infinite sum. So this thing you can you can tie yourself up in logical, philosophical knots trying to think about completing an infinite process. But the way we get around it, or the way we straighten it out, is we say, well, just think about the finite intermediate processes, what values they have, and consider the limiting value of that sequence of intermediate values. So that's the actual definition we give, and that's in definition 2.3, for the sum of an infinite series. Now we're going to end this introduction by looking at a second example. This first example is, in some senses, way too simple and way too easy, in a way. It's got a nice interpretation of just stepping across a distance of 1, stepping half the remaining distance each time. It's got an easy way to picture it, and an easy way to convince yourself that the value which you have is 1. And I kind of gave this, I maybe tried to persuade you here, that the fact that the things you're adding up are getting smaller and smaller, in some senses that explains why this infinite series has a finite sum. The things that you're adding up are getting smaller and smaller, so it's possible that when you accumulate them all in the sum, it does come to a finite value. But a crucial thing to appreciate early on is that isn't enough. So here's another sum, another series. This time we're doing the sum from m equals 1 to infinity of 1 over m. So that's 1 plus a half plus a third plus a quarter, etc., etc. On the surface, on the face of it, this bears a lot of similarities to adding up the powers of a half. The things you're adding up, the 1 over m's, they are converging to 0 as m goes to infinity. Elements of the series are getting smaller and smaller. So we may be tempted to think that this infinite series, maybe that has a finite value as well. Okay. If you ask the computer to add up 10 billion of these, it's still a relatively small value, and of course the value is changing. The amount by which the value is changing, when you add on each new term 1 over m, it's hardly changing at all. These things are getting tiny, tiny. But we can give a relatively good argument in simple terms to show that this series cannot be converging to a finite value. We'll argue by grouping its terms in a certain way. So the way we're going to group them is as follows. We'll leave the first two alone. But then we're going to group together the third and the quarter. We'll leave the 1 and the half alone. Then we group together the next two. Then we're going to group together the next 4. Then we're going to group together the next 8, which will take us to 1 over 16. Then we're going to group together the next 32, which will take us from 1 over 17. Sorry, we're grouping together the next 8. Here we're grouping together the next 16, which will take us from 1 over 17 to 1 over 32. And we keep on going like this. Double the size of the group at each stage. Leave the first two elements alone, then we group 2, group 4, group 8, group 16. At each stage, double the size of the group. We haven't changed the series, it's still the same series of terms, but we're just parceling together the elements in a certain way. And we've done this in a particular way. Sorry, this isn't equals. You see, instead of a third and a quarter, what if I replace the third by a quarter? And in the next group, which has got 4 things in it, what if I replace them all by an 8? And in the next group, which has 8 things in it, what if I replace them all by 1 over 16? And in the next group, replace them all by 1 over 32. So what we're doing is, in each group, we're replacing each element, each term, by the last term from that group. So instead of a third and a quarter, I've got a quarter and a quarter. Instead of a fifth, sixth, seventh, and eighth, I've got an eighth, eighth. So replace each element by the last member of the group. Find the term from its group. And what have we done to the value? When you replace a third by a quarter is smaller than the third. When you replace a fifth, a sixth, a seventh, and an eighth, you're replacing them with an eighth, which is smaller than all of them. So the relationship is that our new value, whatever it has, is smaller than the value that came before it. So the relation is greater than. Our infinite sum is greater than this. But this we can attach, we know precisely what the value of each group is. You've got 1, a half, then you've got 2 quarters, which is of course a half. And you've got 4 eighths, which is of course a half. You've got 8 sixteenths, which is of course a half. 16 32nds, which is of course a half. So each group in this adjusted sum, each group has value a half. Just simple arithmetic fractions. 2 quarters, 4 eighths, 8 sixteenths, 16 32nds, 32 64ths, 64 128ths, etc. Now what value does this infinite series have? Okay, the original series is infinite. So although our groups are getting bigger, there's an infinite number of terms, so we can always form the next group. There's nothing to stop us forming the next group each time. So there's nothing to stop us generating halves. So what's the value of this sum here? You've got an infinite number of halves that you add up. Well, it doesn't have a finite value. You take an infinite number of steps of distance half a meter, you're going to go forever. So this sum grows without upper bound. I.e., it's divergent. And since the series we were interested in, the sum of the terms 1 over n, since this is always bigger than this series, also grows without upper bound. I.e., it's divergent. So although I maybe tried to slip it by you or convince you at the beginning that because the things you're adding up are getting smaller and smaller and smaller and converging to 0, but they're not converging to 0 fast enough. They take their time with that. And what that means is they still have enough weight, there's still enough significance to these terms, so that in the infinite series is actually divergent. So if you wanted to wait around, if you had the ability to wait around as long as you wanted, you would see this sum get as big as you wanted. If you set some ginormous number, if you can wait around long enough, you'll see this summation process eventually get past that value. Okay? Because it grows without upper bound. Because you can always generate another half by grouping together a certain number of following terms. So the terms do not get small fast enough. The terms of 1 over 2 to the power n do get small fast enough, so that the infinite series converges at So this series has got a nice name, it's got a special name. This is called a harmonic series. Term associated to music. If you're familiar with music, you play a musical instrument, you know that in a vibrating string there are harmonics at position a half, at position at all the multiples of a quarter, a various harmonic, all the multiples of an eighth, so on. You play guitar or violin or something, when you dampen the string, not when you shorten. If you shorten the string of the fretboard, it's a shorter string, so it has a different note. If you just dampen the guitar string halfway along its length, not press it down to the fretboard, just rest your finger on it so the middle point can't vibrate, it's held stationary, then the whole string can still vibrate because the left half vibrates and the other half vibrate. So it can still sound a note. And when you dampen it at position quarter, the string will still vibrate and give a note. So that's where the term harmonic series comes from. These fractions are the positions of all the harmonics in a vibrating string. So it's because of this subtlety that the thing only diverges, or the thing only converges if things get small fast enough. It's because of this subtlety that there's a whole lot to study there in the series. So we'll begin that in earnest next week. Better stop now, so I've done a little bit over.